Hello, my name is Andre, and in the next 10 minutes, I want to give you an intuitive understanding of our ACL 2025 paper, Training Dynamics Underlying Language Model Scaling Laws, Loss Deceleration, and Zero-Sum Learning. In this paper, we try to address an important but underexplored research question. How does scaling improve language models, specifically in terms of training dynamics? In asking this question, our goal is to identify mechanisms that are responsible for scaling improvements, but that can be targeted directly and independent of scale. So, what did we end up finding? In terms of training dynamics, we found two phenomena that underlie scaling improvements: loss deceleration and zero-sum learning. And to be clear, this is terminology that we introduce in the paper. To the best of our knowledge, there is no prior work on either of these. First, let's look at loss deceleration. This might not surprise you, but deceleration is basically an abrupt slowdown in the rate of loss improvement. It usually happens quite early in training too, around 5,000 steps. What makes loss deceleration interesting is a characteristic piecewise linearity in loss curves. I say interesting because this piecewise linearity suggests an underlying transition in training dynamics that we know nothing about. Beyond this unknown transition, loss deceleration is also interesting for another reason. Its mitigation can measurably account for and explain scaling improvements. What do I mean? In the figure, we can see that scaling improvements from the small model in purple to the large model in orange are almost entirely attributable to two ways in which scaling mitigates deceleration. 1. Scaling decreases the loss at which deceleration occurs. And 2. Scaling increases the rate of loss improvements, or the slope, after deceleration. In other words, the mechanism underlying loss deceleration and its mitigation by scale also underlies scaling improvements. And that is what zero-sum learning is, a mechanism underlying loss deceleration. In zero-sum learning, a language model can't improve loss on one set of examples without harming it on another set of examples. When deceleration happens, what's going on is that zero-sum learning kicks in and bottlenecks overall loss improvements, which is the sum of these per example loss changes. What's going on under the hood during zero-sum learning is that per example gradients become systematically opposed. As a result, weight updates are aligned with some gradients, but similarly opposed with others. Under first-order dynamics, this leads to the positive and negative changes in per example loss that we saw earlier. Last but not least, we find that scaling mitigates zero-sum learning in a way that explains, at least in part, how scaling mitigates loss deceleration and therefore improves loss, specifically by improving the rate of loss change, or the slope, after deceleration. And so to recap this high-level overview of our paper, first, we wanted to understand how scaling improves language models in terms of training dynamics. We identified two novel phenomena in training dynamics: loss deceleration and zero-sum learning. And we showed how scaling improvements can be explained in terms of mitigating these two phenomena. And just to reiterate, this mechanism of improving loss by mitigating ZSL, zero-sum learning, and loss deceleration is significant because by being based on training dynamics, it could potentially be targeted directly and independent of scale, for example, with optimization methods. All right, now let's look at some actual results. First, looking at loss deceleration, we find empirically that deceleration occurs consistently across scales from 14 million to 7 billion parameter models. To measure deceleration, we fit broken neural scaling laws, or BNSL. These parametrically capture and describe the piecewise linearity of deceleration. In particular, we can recover the following measurements: LD, loss at deceleration; TD, step at deceleration; and RD, the log-log slope after deceleration, shown here on the right. From these measurements, we can fully explain and predict final loss with high accuracy across scales. Because loss is a function of these measurements, scaling improvements are also a function of deceleration mitigation as measured by changes in these measurements. First, the decrease in loss, LD. Second, the decrease in the step, TD. And third, the increase in RD, the slope after deceleration. So, if you can understand what goes on in deceleration and how scaling mitigates deceleration through these measurements, Then we can understand how scaling improves loss. I mentioned in the overview that zero-sum learning is the mechanism underlying deceleration. How do we actually go about showing that this is the case? In terms of per example change in loss, delta L small, there are two possible mechanisms for deceleration as measured by the reduction in overall loss improvements. First, learning and loss improvements could just be slowing down across examples. Alternatively, there could be zero-sum learning, where per example changes in loss cancel out in increasing proportions and bottleneck overall loss improvements. The key insight here, if we want to confirm ZSL is responsible for deceleration, is that both of these mechanisms can be measured and the role in deceleration quantified. Deceleration is measurable as reduced overall loss improvements labeled here with 1. M, the average magnitude of per example change in loss, captures the alternative mechanism where loss improvements slow across examples, labeled here with 2. D, the destructive interference between per example change in loss, captures our hypothesized ZSL mechanism, labeled here in 3. Intuitively, D measures the proportion with which elements in a sum cancel out. It approaches 1 when they cancel out completely, and 0 when there is no destructive interference whatsoever. We can measure and visualize training trajectories with respect to these 3 values. Here, in the plot on the left, loss improvements are plotted as the z-axis color scale. Average magnitude M is the y-axis, and destructive interference D is the x-axis. With this figure, we can visually quantify how changes in one variable affect another. If we zoom in on the training trajectories after deceleration, we see that loss improvements delta L drop by several orders of magnitude. Most of this drop is attributable to zero-sum learning as measured by D approaching 1. D accounts for an 8 to 32-fold reduction in overall loss improvements. In comparison, M only accounts for a 2-fold reduction at most. In other words, ZSL is the main bottleneck responsible for loss deceleration, and quantifiably so. While there's not enough time to go over it in this presentation, we use a very similar approach to show that gradient opposition is responsible for zero-sum learning. First, we define and measure the mechanisms. Second, we derive the functional relationship between mechanisms and phenomenon from first principles. And third, we quantify the effect of mechanisms on the phenomenon using the derived function and empirical measurements. Finally, I want to go over some empirical results that show how scaling improves loss in terms of training dynamics. First, scaling mitigates gradient opposition. We measure gradient opposition as destructive interference in per example gradients across parameters. Each plot on the left is a histogram for these measurements at different time steps. The top 3 plots are time steps before deceleration, and the bottom 3 after deceleration. On the x-axis, we have destructive interference, where lower values represent less gradient opposition. On the y-axis, we have the number of parameters with a given gradient destructive interference in log scale. The main takeaway in these plots is that after deceleration, larger models consistently have more parameters with less gradient interference. Intuitively, each of these parameters is a degree of freedom for weight updates with reduced ZSL. As a result of this, by mitigating gradient opposition, scaling also mitigates zero-sum learning after deceleration. In this figure, the x-axis is training steps with deceleration marked in gray. The y-axis is destructive interference and loss improvements as a measure of ZSL. Larger models are again shown in orange, with smaller models in purple. And so we see that scaling reduces destructive interference after deceleration consistently. In other words, per example loss changes cancel out in smaller proportions and do not bottleneck overall loss improvements as much. And therefore, by mitigating zero-sum learning, scaling also mitigates deceleration, specifically by improving the rate of loss improvement after deceleration, which we showed is responsible, at least in part, for the improved final loss. All right, so this concludes our presentation. Beyond our findings, there are still important unanswered questions. First, how can we, in practice, mitigate zero-sum learning directly to improve language models independent of scale? Second, the mechanisms we identify are not exhaustive, and there are likely other mechanisms that quantifiably contribute to scaling improvements. What are these mechanisms remains an open question. Lastly, zero-sum learning is interesting beyond explaining scaling improvements. Preliminary results in our appendix suggest that zero-sum learning plays an important role in generalization, but it's not clear how or why. And with that, thank you for your time and your attention.